to introduce to you, if you don't already know him, John Debes, who was a postdoc here. So sadly, I guess I've been here long enough that I thought it was much more recently than it actually turned out to be. But he was a postdoc here after getting his Ph.D. at Penn State in 2005. He came here from 2005 to 2008. For his Ph.D., he had worked on the dynamics of planets around white dwarfs and what might happen at the end of stellar evolution. I like to take credit for convincing him that studying disks was an interesting thing to do, and you'll see he's still doing that now. But he's worked on a really interesting and wide variety of topics having to do with planetary systems all the way from their infancy through the end of the stellar lifetime. So from forming the youngest planets around disks to disrupting planetary systems around white dwarfs, looked for companions around white dwarfs, looked for hot dust around white dwarfs, led a huge survey with the WISE spacecraft looking for dusty white dwarfs and nearby white dwarfs. So I think most of which he isn't going to talk about today, but if you have questions about that, there are still some slots on his schedule today probably. So after leaving DTM in 2008, he went to Goddard, as many of our postdocs do, and took up a NASA postdoctoral program fellowship there. And from there went to Space Telescope Science Institute, where he's risen through the ranks of the Space Telescope Imaging spectrograph ranks, so he's now the team leader for that instrument on HST, and you'll get to see how he's putting that to good use today too. It's been a pleasure to collaborate with him throughout all of those years, and now hopefully he's going to continue doing great work at Space Telescope, where he's been since 2011. So we just had to drag him down from Baltimore today, so thanks for coming.
I survived the traffic. So yeah, and I heard I'm the first speaker for your series this year, so it can only get better from here. Well, it's great to be back. I actually was here in July because we did a little local disks meeting where the local disk people get together and talk about all kinds of fun things. So I apologize, you'll recognize some of the slides from that meeting, but hopefully I have enough new stuff to keep you interested. And yeah, it's a real pleasure to be back because this was a really fun time in my career. And as Alicia says, she can take full credit for getting me interested in these kinds of disks anyway, since I was focused on the old white dwarf disks for so long. But it's nice to have two different foci in your research, so that when one is kind of boring for a while, you can move on to the next one, and so on and so forth. So today I'll be talking primarily about sort of what the near term and the future might look like for us in terms of understanding planetary systems, specifically by using space telescopes with high contrast imaging, because this is something that I've been getting into a lot recently. So I'll talk a little bit about some data, some interesting data that I have using the STIS coronagraph on Hubble, and then I'll talk a little bit about what the future prospects for high contrast imaging with Hubble will be as it enters its 26th or 27th year of operation. And then toward the end, we'll talk a little bit, very briefly, about where we might go from here on our march toward ever larger telescopes in space that can do faint imaging of faint things close to really bright stars. And this is all driven by our interest in understanding how planets form and how many of them are like Earth, so where did we come from and who's out there are kind of these two questions that are really driving a lot of planet formation and exoplanet science these days. And so high contrast imaging is going to be a pretty big part of that process. And I have here a list of all the people that I've been working with, particularly on this object TW Hydra that I'll be talking about at the beginning. Okay, so we're now in a really exciting time. I'm sure every disk and exoplanet talk has made that claim in the last 15 or 20 years, but this is, I think, particularly true now, and it will continue to be more true in the future. But we are in this really remarkable time where we're getting spatially resolved images of disks from the very earliest stages of planet formation all the way out to when planets have fully formed and are actually interacting with remnant disks at a variety of wavelengths. So back in the day, we were lucky if we could look at a few handful of disks with Hubble, or maybe from really advanced adaptive optics on the ground in the near infrared and the optical. And now we're pushing out to many more different kinds of wavelengths, from the mid-infrared in a couple of years with James Webb Space Telescope, And in the submillimeter, here, this is a picture of what I'm showing from ALMA, right? So the submillimeter wavelengths probe pebbles, essentially, these larger dust grains that tend to concentrate in the midplanes of protoplanetary disks. These disks are often optically thick to view from shorter wavelengths. And so if you really want to understand the sort of baseline midplane structure of disks that are forming planets, you need to go to these longer wavelengths. And ALMA, with its combination of sensitivity and spatial resolution, it can resolve things at sort of the 100 milliarcsecond level, so that's a tenth of an arcsecond. You can probe into sort of these tens of AU distances from stars that are actively potentially forming planets, and we see these very interesting gaps and rings in the disks. We still don't quite know what they all mean. These could be due to planets, they could be due to changes in the chemistry in the disks, they could be due to these sorts of you can get clumping and runaway effects that can cause sort of interesting pressure structures in the disk. So we're really just getting started at understanding what these pictures are telling us and how they feed into our understanding of these disks earlier on, which were primarily led by unresolved photometry of stars. And that sort of unresolved photometry gave us some idea of the broad picture of what the disks may look like, but these spatially resolved images really tell us what we're seeing. It's very exciting. So this is HL Tau. This was a pretty remarkable image that was put out by ALMA, I guess, almost a year and a half ago. And it really just demonstrates the ability that these high-resolution modes with ALMA can provide us in terms of understanding sort of the inner structure of these protoplanetary disks. So just a little refresher, in case you're not an astronomer who thinks about these things every day. We have a variety of techniques for understanding about both the chemistry and the physical conditions within the disks. And they come from a broad range, all the way from ultraviolet through to mid-infrared and submillimeter observations, and they probe different parts of the disk. So if we have a schematic of a typical protoplanetary disk, we think that a lot of disks seem to show inner gaps or holes where we don't see any dust emission. And that dust emission primarily occurs in sort of the mid to far infrared wavelengths. We probe different spatial scales with different techniques. So there's a lot of interferometry that goes on in both the near infrared, the mid infrared, and at submillimeter wavelengths. These are all using multiple telescopes working together to get very high spatial resolution. But we also have direct imaging that's occurring with both Hubble and large ground-based telescopes like Magellan, for example. And they probe sort of the outer edges of the disk, and they also, in the scattered light, they probe the surface layers of the disk. They can't really penetrate in. That's why you need something like ALMA to go all the way down to sort of the disk midplane. But we think that we have all these interesting structures. We have these gaps. We have sort of a flared type of disk due to hydrostatic equilibrium and also heating from the star. That can cause puffy regions that can then shadow parts of the disk. You can form gaps due to planets, which also create shadows and interesting features. And then there's a real question about what's really happening in these inner parts of the system. Is it really pure gas, or is there still some dust present? How does this look like for each individual star? And then on top of that, you have a lot of information about sort of the chemistry within the disks. And at different wavelengths, you're probing different surface layers. And so you're sort of getting like an onion skin chemistry of these disks by looking at different wavelengths. So there's often, especially with the closest and most well-studied disks, a large wealth of information that you somehow have to put all together and synthesize into a coherent picture about what's going on with these systems. And all of these tell us something about the initial conditions of planet formation, both for giant planets like Jupiter, as well as for rocky terrestrial type planets like the Earth. And the interplay about the chemistry and structure can give us some idea about how a typical planetary architecture may form. And that's really sort of the question that we're starting to answer in a statistical sense with NASA missions like Kepler, where we have thousands of planets, and they tell us something about the demographics of planet formation. What are the results? And these direct observations of the youngest disks tell us something about a snapshot in each period of planet formation. So one of the best studied nearby planet-forming disks is a star called by the name of TW Hydra. This should be a familiar star because Alicia actually put out some HST images of this not that many years ago, but it turned around 2000. And Hubble actually was sort of the first to image and spatially resolve this disk in scattered light. So this is a slightly reworked version of Alicia's original data on the disk, and you can see that it's nearly a perfectly face-on disk. And it may have some structure to it, and it's very close by, so it's about 54 parsecs, 150 light years away. And so you don't have to have a big mirror, a lot of spatial resolution to still learn a lot about this disk and push into sort of a few tens of AU, or what would be comparable to the planet-forming region within our own solar system. So this is a good opportunity to just orient you on the kinds of images we're looking at. So the disk is here, right? It looks like a plate. So you're viewing, right down the barrel of this, and you see the full disk on display. There's no kind of inclination to it or whatnot, so that makes it pretty easy to sort of look at things as a function of azimuth. But because we look at these stars behind coronagraphs, there are often features and parts of the images that are missing simply because of how we're taking the data. So in this particular case, NICMOS, which is the instrument on Hubble that took this image, had a feature where even though you had a coronagraph, it didn't fully suppress the diffraction pattern of the telescope. And so you still had some remnant of the central star at the center of your chronographic image, and you would have these residual diffraction spikes that came from the support structure of the Hubble Space Telescope. And these regions that are blocked out are those regions where those diffraction spikes are much noisier than the actual signal from the disk. So as we get better and better about our chronographic techniques, we get more complete images and higher signal-to-noise images of the disks that we're studying. So at the beginning, when this was all new and there were only a couple of disks that had been spatially resolved, this was sort of the best you could do. And there's some noise in here, but as time has gone on, even with the same instruments and telescopes, we can get better results. So TW Hydra now has been imaged over the past 15 or so years multiple times, and more recently there's been a lot of structure that we seem to see in the scattered light images of the disk. So if you look here, Alicia and I, a few years ago, pointed out, and actually this was mentioned in her original paper, that there seemed to be something interesting going on at 80 AU. So this is 80 AU from the star. You can sort of see there's like a shadowy, darker patch to the disk, and this is what we think is a gap actually in the disk surface, maybe about 30% deep. So that's a little puzzling to have something that looks like maybe it would be formed by a forming planet so far out in this disk, but there may be other explanations for the structure. In any case, that was sort of the first clue that something interesting was going on in this disk. And then a few years ago, the Subaru telescope put out another image of the disk, and this is in polarized near-infrared light, roughly at the H filter band, which is about 1.6 microns per central wavelength. And the interesting thing about the ground, of course, is that you're always fighting against the atmosphere, and so you need adaptive optics to give you a good image of a disk or a planet in orbit. And typically for adaptive optics observations, you also need to do post-processing data techniques, so TJ is familiar with all these, that tend to work really well for sharp features, such as a point source or an edge-on disk, but don't work very well for something like a face-on disk, like TW Hydra. So most post-processing techniques that maybe you've seen, so for like direct imaging of exoplanets with GPI, or Sphere, or MAG-AO on Magellan, a lot of these total intensity, non-polarized imaging really require these fancy post-processing techniques that would wipe, or very nearly wipe, the full signal out from a disk like this. Now you can get past that by looking only in polarized light, because the stars themselves tend to be unpolarized. So if you take an image of a star in polarized light and you have some sort of PSF reference for whatever residual polarization you have, you can get pretty high contrast without needing to resort to post-processing of any kind. And that's how you get a ground-based face-on disk image of TW Hydra down all the way down to a few tenths of an arc second, which for this disk corresponds to 10 or 20 AU, so pretty close. In any case, that's a long way of saying that this group, Akiyama et al., found that there, in addition to the 80 AU gap, which is seen here, and this is a surface brightness profile of the disk. So if you take an average all around the disk and just measure the brightness as a function of radius, you come up with this black line here. And they noticed that it was very kinked in surface brightness, which is a signal that you're seeing a change in the surface of the disk itself. So there's a gap here, that's the 80 AU gap, and then they found evidence for another gap at about 20 AU. And this was followed up with GPI, who also took, Rapson et al. Took GPI images of the disk. So GPI is the Gemini planet imager. And they also took polarimetric images of both the J band and K band, so this is about 1 micron and 2 microns. And again, they detected evidence for a gap sort of at 20 AU. And they also tried to model this in the context of perhaps there's a planet that's carving out this gap at 20 AU. So if you're keeping count, there may be 2 planets all around this disk, or at least 2 structures that are very indicative of something that would be formed by a planet being present. And then, of course, ALMA has taken an image of this disk in submillimeter light, and they found, so this is a different size scale. So the outer edge here roughly corresponds to maybe about here or so. So different size scale, but they found in the inner disk even more gaps, right? So this is roughly, I think, at 20 AU, and this is 12 AU. And then on top of that, there's an inner clearing at about 1 AU, right there. So we now have, let's see, 1, 2, 3, 5 gaps in the system, and this is starting to look a lot like that other disk HL Tau, which had a lot of gaps as well. And so a question is, what is forming all these gaps? Is it really that this is a 5-planet system, or is there something else interesting going on? So, TW Hydra is named Hydra for a reason, right? This is in the constellation of the many-headed mythical creature. Anytime you get more observations of the star, it becomes more complicated, so another head appears once you cut one off, essentially. So I'll take a small digression here on why we want to keep looking in space for high contrast imaging, and this is going to lead into some of the new developments for STIS in particular on Hubble, and where it can sort of feed into high contrast imaging. And that'll lead into the new data that I'm going to show with the STIS for TW Hydra. But basically there's a couple reasons why you might want to go into space. And this is not to knock ground-based observing at all. There's plenty of complementarity between what is being done on the ground and what we can do in space. I mean, the simple fact of the matter is that Hubble is a very limited resource, so you're never going to look at a lot of disks anyway, just by nature of the pressure on the observing time. But when you can go into space, it is preferable for at least certain cases where you need a lot of stability, for example, right? Because you're not correcting any atmosphere in space. So even with much more simple coronagraphs on Hubble, we can do about as well or better than the ground, depending on the particular science case. So that's one reason. Stability. Lack of atmosphere is really a key thing. This is a picture, you can see Hawaii in the path of the 2 hurricanes, right? We don't have to ever worry about weather or bad seeing. We sort of get the same seeing every time as long as we keep our telescope well focused. But that stability and lack of atmosphere are really important for observing from space. And this is actually an image of the focal plane for the STIS instrument and its coronagraphic aperture. So, maybe you've seen a couple of talks where people have shown the latest chronographic designs for 8-meter or 10-meter telescopes like Keck or Magellan. And they're very fancy, right? They have these very carefully constructed occulting masks that you put in the image plane so that you block out the light from the star and you push all the diffraction from the star out beyond in the pupil plane to some another mask that blocks all that excess diffraction out, so you really suppress the light greatly from the star so you can look at the faint stuff around. And then also that's often combined with lots of deformable mirrors that work to both correct the atmosphere's effects on your image as well as any wavefront errors that may be present within your optical system. They will sometimes also have these very nice detectors that are integral field units that look across wavelengths, so you can do a nice post-processing based on changes in wavelength. Well, we have none of that here. STIS was launched on roughly around Valentine's Day in 1997, so it was put up on in the telescope in I think the second or third service ignition, and it was lucky it had a chronograph because, as many things happened in the early days, the chronographic mode of any instrument was often descoped the first thing. So there's no optimization here. It's basically a collection of wedges and bars that you use to just block the light from the star. And then in the pupil plane of the camera, there is a slight undersizing to the pupil so that you get what's called this is basically a very, very, very simple Leo chronograph, in that you have something in the image plane to block out the star, but then you also have something in the pupil plane of the telescope which takes care of some of the residual diffraction that gets sent to the edges of the pupil. So there is a little bit of that there. So the diffraction pattern of the star, what we call the point spread function, is diminished a little bit by going through the camera, but not a lot. It's only a factor of a few that you've depressed things. So if you compare that to things like ground-based instruments like GPI or so, where they get a factor of 100 or 1,000 suppression of the PSF, we don't have that. We have to rely on the stability of the telescope to get the very high contrast that we can, either by rotating the telescope or by picking a reference star that is very similar to the target that we want and subtracting one from the other. Now recently, STIS, even though it's 19 years old, has a new mode, and that's because this neglected BAR5 aperture location finally got commissioned. So when STIS was first built by Bruce Woodgate at Goddard, they had this little very narrow occulting finger that's about 0.3 arcseconds in width. But as this was all being constructed, someone somehow bumped it, or it got knocked or something, and the little finger got bent. And so after that, people were really leery of doing anything with this little bar because they were concerned maybe it wouldn't work well or whatnot. And STIS has about a bajillion different modes, so it's hard to characterize, calibrate, and support all the modes it has. So in the end, this always got ignored, like the sort of red-headed stepchild, until a few years ago, Glenn Schneider and Andras Gaspar at the University of Arizona put in an outsourced calibration program. So they basically said, hey, Space Telescope, we'd really like to make your instrument better. This is what we'd like to do. Are you okay with that? And we said, sure. And so they figured out how to put stars behind here. They demonstrated that it worked with some known debris disks. And now it is a supported mode on Hubble where all you have to do is click a couple buttons and you can use this for your science as well. So even if all you come away from my talk today is that you can propose to do really cool coronography, that would be great, because the more people who propose to use this mode, the better, because that will mean that there's interest from the community in using this, and that gives us the motivation to focus on making these kinds of modes better. But you can see a lot of other different positions on the focal plane. These are other coronographic positions that are supported that you can just select for Hubble, and Hubble will know immediately what to do your coronographic observations. So the images of TW Hydra that I'm going to show make use of this newly commissioned BAR5 location for STIS. The other thing I should mention is STIS is a CCD, and so the chronographic mode of STIS is a very broad bandpass image. It goes from the blue sensitivity of the CCD all the way to the red sensitivity. So you have to have a really good color match between your target star and your maybe PSF reference star to do your PSF subtractions, or else it won't work so well. But anyway, this is an actual image, I think, of TW Hydra behind the Wedge A1.0 position. And this shows you, the star is blocked out. These are the diffraction spikes. And it's, it's kind of a mess. Where's the disk, right? But if you do PSF subtraction here and also at BAR5, you'll notice if I flip back, you actually can get a pretty good amount of coverage just in a single orbit of Hubble. You have to understand that every orbit that Hubble makes, you have about 50 minutes to take your observations, and then you get another orbit. And so what you want to do is, in between each orbit, you want to rotate the telescope a little bit, and that gives you both angular coverage for your target, but it also gives you some protection against any sort of PSF subtraction residuals that you might have, either due to color mismatches or the fact that the telescope changed its state a little bit. All those things together make for pretty pictures with Hubble. But if you have this combination, you basically get a pretty good coverage just in one orbit, and then if you sort of rotate the telescope a little bit, one way or the other, you can almost get full coverage of your target in just these two settings. It's also important to note that you have limits on how much you can rotate the telescope. You can't go 360 degrees between two orbits. You can at most go 10 or 20 degrees. So you're really limited in how much angular coverage you can do in any given program on a target. And that's why earlier STIS images, chronographic images, typically used 1 or 2 orbits, and you had these funny leftover structures. So now, because we've sort of learned over the years how to do this and get the most coverage, and also with this new BAR5, we can actually get much better angular coverage, which I'll show you later. So this is actually another image of data that Alicia was involved in, along with a former DTM postdoc, Aki Roberge, where they took an image of TW Hydra now with STIS, and they took it over 2 spacecraft orientations. So this is the funky pattern that's left over by having that wedge and rotating, and this is what's blocked out. But you can see that you have this nice image of the disk. It extends quite a bit far out. This is actually an image that I reprocessed. So you can get a really good image of the disk, and this was in 2000. So, and then just for reference, this is the Gemini Planet Imager field of view. As we've gotten better and better at coronagraphy, typically we have smaller and smaller fields of view. One, because the telescopes are getting bigger, and so that restricts your usable field of view. But also because ground-based telescopes very often rely on these deformable mirrors to do wavefront correction. They can only correct over a small range of distances from the star. So you're often very limited to just the innermost parts of these big disks. Whereas you can see, we have a lot more information that we can use at our disposal out here as well. So one nice thing about STIS is it has a 50 arcsecond by 50 arcsecond field of view, much much than what can be done from the ground. So if your interest is in big things, STIS is one way to get about doing that.
Where's the 10 AU gap?
The 20 AU gap is 10. The 12 AU gap is probably like right around here,
Okay.
and the 20 AU one would be about here.
Okay.
Yeah.
Thank you.
So this is what we can do now with the combination of BAR5, the Wedge A1.0 position, and many more spacecraft orientations. We can push into about half an arcsecond all around, and we can push as close in as about 0.2 arcseconds. So half an arcsecond is about 27 AU, and 0.2 arcseconds is about 11, 12 AU. So we just get into where the ALMA data shows a gap there. And then we also looked at it again in 2016, but I don't have the image here. But it's really beautiful, I think, anyway, having stared at this for as long as I have. And I should mention this is a logarithmically scaled image, so you can see the scale here in terms of surface brightness. So this is flux density per arc second squared, and you can see that the disk is sort of trailing off in brightness as you get further out. But there's sort of that hint, and even in the logarithmic scaling, of that 80 AU gap. Okay, now if we do a surface brightness profile, we see from all the way out from a few tenths of an arc second all the way out to 7 or 8 arc seconds that this disk is detected. It shows a few kinks here, 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 right? This is the 80 AU gap. This is, we confirm there's definitely a 20 AU, 20 business going on, and then we see that the disk continues up. And we don't see any big changes between 2000 and 15 years later. So that's the first thing you would want to check is, has anything changed broadly in the disk? But averaged over all angles, nothing seems to have changed too much. It's basically the same. And we can compare with the other data that has been, other images that we've looked at with the disk. For example, so this is the ALMA surface brightness. So this is thermal emission, so it's a little bit different here. This is roughly tracing temperature and density. Okay, and then I've normalized the surface brightness of the disk to highlight features in the scattered light. And basically all I've done is I've taken out the 1 over r squared dimming of, as you get further and further away from your star, the overall light that gets scattered into your direction of viewing is diminished by 1 over r squared, simply by the fact that you're farther and farther away from the star. So I've taken that out, so I really highlight sort of the surface wiggles and bumps of the star, or of the disk in scattered light, and you can see that both the polarized GPi data and the STIS data lie right on top of each other until you get about to 10 or 20 AU. But there's really good agreement, and you can see that there's a little bit of a correlation in this sort of kink here, that 20 AU gap, with some features that are seen in the submillimeter as well. There's sort of an offset there, but perhaps these two features are related to each other in some way. You can also now, since there have been so many images of TW hydro taken over many different wavelengths, you can look at the spectra of the scattered light from the disk. How efficiently does the disk scatter light as a function of wavelength, as a function of distance in the disk. So this was some results that we put out in 2013. Basically, the spectrum is a little boring. It's sort of like a blue trend in the sense that it's a little bit brighter at shorter wavelengths than at longer wavelengths. But now with the new BAR5 data, you can push much closer in to sort of 20 AU or so, and you notice that it's getting a little bit bluer as you get closer to the star. So what we need are radiative transfer models of this disk to really understand what this may be telling us about the chemistry and the surface of the disk. So if we do that 1 over r squared trick to the whole disk, you can really see in the images also the gap at 80 AU. And then if we go to 2015, where you have much more coverage, you can see the gap. They're also seen, this is sort of the 20 AU gap. Now for us, we don't see the disk really recovering. It seems like it's in shadow in this inner region. You would expect sort of a disk to be getting brighter, at least as 1 over r squared, right? Because as you get closer to the disk, if it has roughly the same shape and amount of material, but we don't see that in the interior. So there's something that's sort of, at least in the optical, shadowing this inner region of the disk somehow.
Is the asymmetry in the gap real?
This?
Well, the fact that you go more blue on the top left.
Yeah, I will argue that's real, and I'll show you some figures. And I'm just going to do that. Looks like it moves, right? Okay. So if we do a careful job of looking at the azimuthal profile of the disk at different radii, we do indeed see that there are asymmetries as a function of angle in the disk. This is surface brightness normalized by the local surface brightness, so you can sort of average over different radii very carefully and put them all sort of on the same scale, and we see sort of a 10 to 20% asymmetry in the surface brightness as a function of position angle in the disk. Pretty consistently, and from epoch to epoch, you know, if you really squint, you can convince yourself that the peaks between 2015 and 2016 are not quite lined up. And I'll show you that in this next figure. So if you model that asymmetry just as sort of a sinusoidal profile, you get you know, where the position angle of that peak. And I should say that Aki and Alicia saw this azimuthal asymmetry in 2000. And since they only had one epoch, they attributed this to either a warp in the disk that was, you know, changing the overall surface brightness as a function of angle, you know, right? So at some radii, your disk was sort of more inclined than you would think. So you can get these asymmetries just from the overall structure of the disk. A natural flared, slightly inclined disk will show an azimuthal asymmetry just due to inclination effects, and not due to anything else. And so that was sort of what they attributed to, or perhaps forward scattering of dust grains, both of which are very reasonable explanations when you have one epoch. But the problem is that the position moved by almost 20 degrees. The position of that peak moved by almost 20 degrees in 1 year. That's pretty fast. And you can't explain that by a static structural inclination effect or due to forward scattering, because both of those things would stay constant with time. You can notice, however, that in the inner system there is no movement, apparently. So there's a range of radii in the disks where you see the same asymmetry and it's moving in the same coherent fashion, which is somewhat puzzling. Okay, if we can look at only one radius, but as a function of time, we can look for this asymmetry in other data that has been taken of 2W Hydra with Hubble in the archive. And so in the end, we were able to pull out data from Alicia's old program in 1998, 2000, another program of hers in 2005, which isn't shown here, as well as another image of the disk in polarized light that was taken with Nick Moss in 2004. And they all show the same pattern, but you can see that the peak has moved around with time. Now this is not totally crazy. There have been other examples where we've seen moving features in disks. So I'll just call out one example here, which also used STIS. And this is for the debris disk AU microscopy, so a different kind of disk. But what they found was that there were clumps in the disk that were moving out with time radially. So we don't see this behavior necessarily, but we are starting to see in our data, as we take more and higher quality images of disks, that disks are not static, that they're moving, they're changing, the illumination on them is changing, and that is leading to constraints on some of the physical processes that may be going on in these dusty disks. Okay, so if we put all of the data on a line, we see that the position angle is increasing with time, and then it sort of cycles over and increases again. And when you fit this line to all of the data, so we have all the different radii in the different colors, and then if you take the average of those radii, you get the gray points, and I've estimated the errors on each point by the spread in the data that we have. And we can see a very nice linear relationship. Basically, it's rotating in a counterclockwise fashion, which we can see here. So this is basically taking a surface brightness profile of the disk and rotating it around in angle, and imprinting an azimuthal asymmetry, and then putting it on the time scale that we're actually seeing from our data, this rotation. Now I've exaggerated the asymmetry by a factor of 2, so you can just see it moving around, but this is essentially what we think has been happening from 1998, that it's just going around, and we're sort of in the next, we've gone through 1.5 cycles, essentially. So by 2029, we'll come right back around to where we were in 1998. This is incredibly confusing, though, because this is 16 years, right? A disk at 100 AU is moving at a much slower speed. You know, Pluto takes a few hundred years to go around, and that's not nearly at the distances that we're seeing this moving. So whatever is happening, it's not happening in the outer disk. It's an imprint from the inner structure on the outer part of the disk, and we're seeing it move. So we're actually looking at a shadow moving around the disk from the inner system. And this is not entirely surprising. You know, Aki and Alicia mentioned that a warp might be causing this asymmetry. Rosenfeld et al. In 2012 noticed that the the gas in the disk was rotating much faster in the inner part of the disk than you would expect, and so she invoked a warp in the disk that was somehow speeding everything up for the CO gas. And if she took that warp model and made a radiative transfer of the scattered light, she found that sure enough you could get an asymmetry of the right level from a warped disk. So perhaps there's a warped disk in the inner system that's rotating, and this shadow is showing that rotation of the inner disk. So we have a lot of constraints from the ALMA data on where there might be these warped disks, right? You would expect them to correlate with one of those gaps. And the time scale, if it's due to sort of the precession or rotation of a warp or an inclined disk, also gives you some constraints on what could be causing that. So if you assume that you have a planet that maybe is inclined a little bit from the main disk, and it's warping things sort of in this inner region, maybe at about half an AU, right around that 1 AU gap, you get sort of the right time scales for this precession time scale of about 16 years, and you only need about a 2.5 mass Jupiter planet to make that happen at 1 AU. But what happens is some of the light rays from the star get blocked by this inclined disk, and that imprints a shadow on the outer disk. But if it's inclined enough, it'll skirt on through to the inner part of the disk. So that's why we don't see any motion of the asymmetry in the inner part of the disk. We're merely seeing the asymmetry that you get from inclination that's staying put, and it's still just being perhaps irradiated by the star. But as you get beyond 30 or 40 AU, you start hitting the shadow of this inner disk that's moving around. So
Why would an object of that mass be outside the plane of the disk?
Alicia asked me that question this morning. I don't have a good answer. I was just happy that I figured out a scenario that would fit the observations. Now, the inclination that I'm talking about is only about 10 or 15 degrees, which is not crazy different from what we see in our own solar system. It's maybe a factor of 5 larger.
Big B is also misaligned.
Right, right. What, I don't know, what's the misalignment for beta?
Like 70 degrees or something.
Yeah. So, and of course, the actual inclination is highly dependent on what you think the surface, how high up the surface of the disk is. If the TW Hydra disk is much thinner than I'm thinking, then you can get a much lower relative inclination still creating the shadow effect. So it's somewhat dependent on what you think the vertical height of the disk actually is, which is somewhat hard to get at observationally. You have to use a model to sort of predict where that would be. So the exact inclination and mass are somewhat dependent. Mass is not going to change too much if you're at the same distance, but it will change somewhat on what your assumptions of inclination might be.
So could you just explain why something of 1 AU would have to give you a period of, was it 8 or 16 years?
Yeah, so that's a precession period. So if you think about the paper that you want to look at is Dong Lai, 2014, where he looks at what are the torques and angular momenta associated with a star disk combination with an exterior perturber that's inclined by somewhat. What happens is the perturber torques the disk out of its natural plane, and that causes it to precess a bit. And that's always going to be a bit longer than your orbital period, just because it's a different mechanism rather than just, you don't have enough mass to just directly pull the disk with it. It's always lagging a little bit, and so you get this slight precession effect. So that's why it's much longer. So if you inferred a Keplerian orbital period to that 15 or 16 years, that would put you at about 5 AU from TW Hydra. At least from what we can tell in the ALMA data and the scattered light data that we have, there's no obvious features at 5 AU that would suggest that that's where things are happening. If there was something at 5 AU, maybe puffing the disk up or pulling it along with it, you could maybe imagine like spiral waves being caused by a massive object. But anything massive enough to cause spiral waves would also cause some sort of observable gap feature as far as we know. So that's why I favor sort of something much more interior. Also, if you have something interior, you don't need as big or as high up a structure to still get the shadowing that we see. So this is by no means a solved problem, but I'm trying to like put all these little pieces together to come up with a plausible scenario for what might be happening in this. Interestingly, a 2.5 mass Jupiter planet would be large enough to create a somewhat measurable radial velocity signature with a period of about a year, 1.2 years. And the signature would be smaller than what has actually been constrained to be existing for TW Hydra, because people have looked at TW Hydra with radial velocity, the radial velocity technique, and there had been a claim of a hot Jupiter in the system, which was then debunked as being due to star spots. So if you looked at TW Hydra in the near infrared for radial velocities, you would definitely see, and you had enough sensitivity, you could actually constrain this scenario observationally, which is kind of cool.
Can you estimate the age of a disk by knowing its thickness?
Usually we estimate ages from a different way around. So TW Hydra is part of a loose association of stars where the ages of some of the other stars are pretty well known, and also just based on the luminosity and temperature of this object, we have a constraint of about 8 to 10 million years for the age of the system. So it's a little long in the tooth to have such a beautiful protoplanetary disk. Usually we think these things disappear in a few million years. So that's like a whole other talk for another day. But we do have some estimate on how old the system is. You don't have to read the text. Basically, this is weird. We want to understand why it's weird. And of course, because it's TW Hydra, it's yet another weird thing on top of the 15 other weird things about this disk. And I think it's not so much that it's weird, it's one of the few disks that we actually have the ability to look at in detail. And whenever you have enough detail, you figure out that things are always complicated. All right, so the BAR5 aperture on Hubble has motivated me to try to think of new and interesting ways to use this for high contrast imaging as a springboard for what maybe we'll be looking at in the future with future missions like WFIRST or even James Webb, where there are going to be chronographic modes on these future NASA missions in space. And right now, the only space-based chronograph that's functioning is on Hubble in the STIS instrument. So we want to leverage our ability to study what goes on in space now while we still have the time before STIS or Hubble stops working. So one of the ways that we've done that is to try and push the absolute limits of the kind of contrast you can reach with STIS and to see whether this is comparable, complementary, or competitive with what can be currently done on the ground in the near infrared. Because you can imagine if you can get high contrast in the near infrared, you might also want to get high contrast in the visible as a sort of a complementary wavelength regime to learn something about a disk or a faint companion, something like that. So one of the nice things about STIS is it can go all over the sky, so we can have access to northern targets. Right now, most of the very fancy, really good chronographs are all in the southern hemisphere. We have no intrinsic magnitude limits to getting the kind of contrast. We're only limited by our ability to integrate for a certain amount of time, and as well as sort of the sensitivity limits of the telescope. So that can be a plus if you have sort of a faint object that you want a lot of magnitudes of contrast. You can't do that from the ground because typically these very high order corrections really need a lot of photons. And we're one of the few chronographs that can do total intensity visible light. Most chronographs on the ground operate in the near infrared, or if they don't, they tend to operate in polarized modes for the reasons that I was saying earlier, polarized light. So STIS is sort of unique in that ability. And the combination of these three means that there's a specific niche for STIS if you can get high contrasts that are comparable to what's being done on the ground, which is about 10 to the minus 6 contrast within an arcsecond. So the way we did that is we basically took every possible chronographic technique that has been known to date and do it all at once to see if we threw enough things at the wall we would get a good result. So we did lots of spacecraft orientations. We did small sub-pixel dithering behind the mask to improve contrast right at the inner working angle. We looked at a single star, so we were doing what's called azimuthal differential imaging. So we have a perfect color match between our reference PSFs and our target PSFs. And we wanted to see how far you could push down and how close to the photon limit of STIS you could really go. So that all that was really limiting you was your ability to integrate on the wings of the PSF of the star to get your contrast. So we picked a fairly bright 3.6 magnitude star, HD 3393, which will eventually be a direct imaging target for WFIRST or Habex or Louvoir, this is going to be one of those solar type stars that people are going to be interested in because it's so close by. So if we look at it now and we find something that would be useful just by itself for these future missions. But it has no known dusty disk excesses, it has no known exoplanet companions, and so those two things are good in the sense that you want to make sure you actually know what your contrast limits are and you don't have some sort of source getting in your way. So we looked at this with 9 HST orbits as part of a calibration program for STIS, and we tried to get as high a contrast as we possibly could using these post-processing techniques that people use on the ground. I mentioned we do sub-pixel grid dithers, so what that means is for the uncertainty with which we can place a star behind BAR5 is big enough that your contrast degrades right at the edges of the mask, because sometimes your star is misaligned with the mask just a little bit one way or a little bit another way, and when you try to subtract one from the other, that causes a mismatch in the PSF reference. So some other smart people at Space Telescope have developed this technique of doing very small dithers, and if you combine that with post-processing, you can increase your contrast at the very closest inner working angles you have. So that was led by Remy Sumer at the Institute, and they developed this for James Webb. So the nice thing about doing it with STIS is you can have an operational on-sky test of their theory and demonstrate that you get sort of the levels of improvement that they were seeing for their models with James Webb. And they found that you would, if you did this, you get an improvement of a factor of a few at your inner working angle of your coronagraph. So we demonstrated that, first of all, STIS can do very accurate dithers from visit to visit. You know, these are fractions of a pixel, and we make this nice 3x3 dithering pattern that is roughly aligned with the angle of the BAR5. And I'll show later that we actually do get an improvement in contrast of a factor of a few. So this is actually the images, and what I'm showing is the beginning. So the way we do this is we take hundreds of images, right, from all the dither positions, all the orientations, and we make a big library of PSF references. And we combine those in sort of a principal component analysis fashion to create a synthetic PSF that matches the slowly varying conditions in the telescope. So if there are residual features that show up in almost every image, then we can subtract those out very easily, and you're left with, at the end of this movie, you can see it, you have a lot of junk, but then sort of smooths out to this very nice, low noise, high contrast region where you can get really close, you know, a few times 10 to the minus 7 per pixel contrast relative to that star. So these are the per pixel contrasts that are comparable to what we see with GPI and Sphere. So this is work that has been done a lot with by Ben Wren at Johns Hopkins. He did a lot of the post-processing of this data. And so I'll walk you through this. This is the 5 sigma point source contrast. So if we were looking for point sources, we would detect these kinds of point sources at these contrasts with a signal to noise of about 5, which is typically the standard way that we say, okay, we would have seen something. So if you don't do anything to your data, you have sort of this raw contrast, and this is dictated by the wings of the PSF. If you just do classical ADI, which is just subtracting one from the other, making sure you've lined things up properly, and then derotating everything and just averaging, you get this sort of contrast. And ADI is good, but it's very sensitive, especially at the inner working angle, to PSF subtraction residuals, which you make no attempt to get rid of. And then if you do the post-processing techniques, that's this purple line here, where we use CLIP. That's the name of the PCA process that we use. And then we can compare that to sort of one of the better contrast curves from GPI, but in the near infrared. So we actually are doing as well or better than the best that can be done on the ground in terms of contrast. Now, this does not translate into a better sensitivity to planets, because in the visible, planets that are self-luminous are peaking their brightness in the near infrared. So we're not more sensitive to planets, but this extreme contrast is particularly good for any faint stellar companions you might be interested in, or if you wanted to see a very faint disk at these kind of contrasts close to a star. So in the visible, dusty disks light up much better than in the near infrared typically. because in the visible we're sort of at the peak of most solar type stars luminosity. And then just for comparison, we get pretty close to the photon limited contrast right at about 1 AU, and we're within a factor of a few all the way into our inner working angle. So we're doing well. And it seems to suggest that actually classical ADI beyond 1 arcsecond is probably sufficient for most of what you want to do, at least at the levels that we were looking at. But CLIP, the post-processing, does buy you a factor of a few in the interior for STIS. So that's good to know.
John, where's that GPI curve come from?
That was given to me by Laurent Fueyo. So I think this is the contrast curve that they derived for 51 area. He said that bump was 51 area B. So, and so we're getting roughly comparable to GPI at about half an arcsecond. So that's pretty good. And this is just a graph showing the kind of improvements you get with the sub-pixel dithers using different numbers of reference images compared to the photon limit. And basically we're seeing a factor of a few improvement. But this is a good test for what will be happening for the James Webb Space Telescope to get high contrast in the near and mid-infrared. So the fact that we've demonstrated this is useful for the James Webb mission as well. Now the other nice thing is that STIS has, as I said, a large field of view, and it can go very deep. It can actually achieve 10 to the minus 9 contrast, but far from a star. So you can imagine using STIS as a pre-imager for some of the W1 or HabEx or Gouffard targets, because these stars have very high proper motion, right? This star may be over here in 2025 when one of these things launches. And so you can sort of map out all the possible contaminating extragalactic sources in your potential path before you try to spend a lot of 30-meter space telescope time on a target that has a galaxy right next to it. So one thing that STIS could be used for in principle, along with a combination of ground-based assets, is this very deep high contrast imaging as a precursor for some of the other direct imaging missions. So hopefully I'll convince someone to do that project. And this is just a quick look at how deep we can really go with STIS on a couple of typical stellar magnitudes for bright nearby stars. We can get, like I said, 10 to the minus 9 contrast a few couple of arcseconds away, which is deep enough to look for things that would be confused with expected planetary companions in scattered light. This is where W1 will be looking, but if we can see things that are 5 arcseconds away now, they will fall into where W1's field of view will be in 10 years. And this also shows you that STIS, will easily see any stellar object down to very, very old and cool white dwarfs with no problem, all the way down to the inner working angle. And we even have some sensitivity, thanks to our near-infrared sensitivity, to warm, young planets or brown dwarfs. So you could look at a brown dwarf or a planet if you wanted to with STIS.
What is the near-infrared sensitivity? How far does it go?
We extend to about 1 micron.
Okay.
All right, so I'm pretty much out of time, so we'll have to look to the future another day. But all these telescopes will be engaging in high contrast imaging to some degree or another. And I'm involved in the W1 science investigation team, so what I'm trying to do is I'm trying to leverage what we're learning with STIS to what we may want to do with W1. And of course, all of these these telescopes will be cross-pollinating in terms of ideas and techniques, so that we can really squeeze the most out of these images and learn at the most we possibly can about how planets form and where they're located in the local galaxy.
Is there a funding problem with W1?
Is there a funding problem? There's always a funding problem to some degree. Right now we're looking pretty good because Congress keeps giving us money, even though I think the president keeps asking for less money for this mission. So for the time being, things look reasonably good for W1. It's still early days, but NASA has officially made this a priority and a mission that's going to be going forward. So I think as long as NASA's committed to this mission, they will find one way by hook or crook to make it launch. Modulo Congress, presidential people, that sort of thing. Society, Anyway, thank you very much. Appreciate it.
Questions for Don?
Serge.
So is the spectroscopic coronagraph mode officially supported on STIS?
For STIS?
The fiducial bars?
Right, so one of the fiducial bars is officially supported, but I guess what do you mean by that? It'll go through the pipeline.
So the second part of the question is,
Yeah.
does it help any? I mean, could you do spectroscopy to
Yes.
any of the extent that
Yeah.
you're doing here?
Yeah, the Jessica sitting next to you is really the person who asked about that.
Right, yeah, so I mean, there are certainly more things that we could investigate doing with STIS, and I happily encourage anyone in this room to think about what that might be. But, you know, go to the instrument handbook on STIS, look for something. I don't think people realize that they can make proposals to just do better calibrations with the instrument. So Andras and Glenn, they got funded and they got telescope time to make STIS better, and that's a somewhat different process than the main scientific tack that people go through when they propose for Hubble. So if you have an interesting idea like coronagraphic spectroscopy where you think you can do better than what we're doing at the Institute, the simple fact of the matter is we have many priorities and not enough people. So we can't do everything by ourselves to make every mode of every instrument completely worthwhile. We follow where the majority of the accepted time is going. And to be honest, that's not going to high contrast imaging at the moment. It's a small fraction of everything that STIS does because it has ultraviolet imagers, it has ultraviolet spectrographs, it has a lot of different modes, and a lot of different science cases get used with STIS. So the way to really jumpstart something, if you're particularly interested in seeing something happen, is by proposing to do it yourself, because then that pushes or just yelling at us. That also works. We try very hard to respond to what the community is telling us, and if there's a large group of people saying, we need this looked at, then I can go to my bosses and say, look, I've got 15 people yelling at me because I'm not doing this, and they'll be like, okay, make it a priority. It's not that easy, but that can be done if we have community involvement. So I strongly suggest anyone in this room who has a good idea for high contrast imaging or spectroscopy, come talk to me or propose something, and we would be, that's how we get things happening. I can only push John likes high contrast imaging so much before they stop giving me calibration time. So it helps when there's external people. But the short answer is there's no good, easy tools to do high contrast spectroscopy right now. Not many people have used it. So it's sort of like a chicken and egg problem.
We do know.
Alicia's the only one who's...
Hockey,
and
Jessica
hockey.
and I know how.
Yeah, that's about it at this point, I
Yeah.
think.
Almost, yeah. Cool.
Going back to CW hydras, is there any evidence for disk winds and whether those could be shadowing, causing shadowing if they're not on Debes?
Sure, it's certainly possible. There have been a few people that have looked at the impact of disk winds launching surface dust grains above the midplane, and that presumably would have an effect. I don't have a good sense of how much dust you would have to lift up to start showing sort of a 20% effect that happens to coherently rotate. My sense of disk winds is that they would maybe be clumpy, but they would be primarily radial in their motion. So you'd have to figure out a mechanism that looks like a rotational effect for clumps, and I don't have a good sense of that. I mean, it seems like that would also be much faster, perhaps, like shorter term.
At 5 AU rather than
Sure, yeah, I mean, I guess if there was like a localized region that was launching up, and that just moves with the disk, that's...
Although I was pointing out to John earlier that this has to be really optically thick because we don't see much color difference. Like if you're just shielding the star a little bit, you would expect to see red light hitting the outer part of the disk and not blue light. And at most there's a tiny bit of reddening, so it has to be pretty optically thick.
Yeah, that's a good point.
I don't know how much dust you can raise that way. There is evidence, I think, in the neon line from Ilaria. I think Ilaria Pascucci detected this neon line from TW Hydra that is evidence of a wind. But
Yeah, I mean, the disk is photoevaporating at some level. But that is definitely an area of study that needs to be looked at more carefully to understand what's going on.
Questions? Okay, well, John will be here today. If you're not on his schedule and you want to be, let me know. And otherwise, let's thank you for next time. I remember calculating what the rate is. I don't remember it at the moment.
I want to say like 1.2 solar radii or something like that.
I remember it.
Oh, you mean the disk?
No, the disk, the photoevaporation, right?
Oh, yeah, it must be fairly close because it's a low-mass star.
Right.
I just want to say hello, Steve Merritt.
Oh, hi, Steve.
I was a co-I on STS.
Oh, great.
And I also was the guy who included Bruce Whitney in the Dithers.
Ah, nice.
That was a good
Project
Thank
he
you.
worked on. I mean, that was actually for Solar Max mission.
Mm-hmm.
But any interest